Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. We're actually starting a new unit today. It's our unit on transformations, although we'll talk about transformations in some other units as well. Before we get started with any new material, let's do a couple of review problems. You have 4 problems here, and take the next 3 or 4 minutes, pause the video, and see how many of these you can get done. Alright, so it says draw an obtuse angle. And we should know that an obtuse angle is an angle that has a measurement greater than 90 but less than 180. So it makes sense to put a measurement here, unless you're going to say it's drawn to scale. But that would be an example of an obtuse angle. It says draw and label 2 vertical angles. Well, remember, vertical angles are angles formed by 2 intersecting lines, and they're the angles across from one another. So the top and the bottom angles would be vertical. If they're vertical, we know they're also congruent, so that's why I put the 2 arcs there. But we also have 2 vertical angles here on the left and right hand sides, and those 2 would also be congruent. All right, let's go with number 3. We have an equation here and they're asking us to solve it. But this equation may look different than any equation you've actually seen before. You may never have seen an equation like this because we see a comma here and a comma here. Well, we also see a set of parentheses, and when we have a set of parentheses and 2 terms inside separated by a comma, we should think ordered pair, right? So we're being given an ordered pair here, 3 comma negative 2, and we need to solve the other ordered pair to figure out what x and y should be. So based on our ordered pair, the x values of each ordered pair should be equal if the ordered pairs are equal. And the y values of each ordered pair should be equal if the ordered pairs are equal. So I have 2 equations. I have 3 equals x plus 1, and I have negative 2 is equal to y minus 3. Right? Basically, this equation is saying that we have a point on the left-hand side that's the same point on the right-hand side, which means the coordinates have to be equal to one another. So I solve this, I get x is equal to 2. And I solve my other equation, I get y is equal to 1. Now again, that's not what the coordinate is, that's just what the x and y value in our equation is. The coordinates for both points are 3. The x coordinates for both points are 3. The y coordinates for both points are negative 2. All right, number 4. There could have been a lot of answers for this. You may have talked about different types of transformations in a middle school geometry class, or maybe even your algebra class. You may have thought transformations of shapes, right? Maybe you thought of a rotation or a reflection or a translation. Those are the 3 big ones that we usually learn first. But maybe, depending on how far you got in your Algebra 1 curriculum and how in-depth you went into certain topics, you may have talked about transformations of functions. So transformations aren't specific just to geometry and just to shapes, right? We can perform transformations on other things as well, and functions is just an example of one of those things. Okay, let's start to get in for the vocab today, and then we'll see if we have some practice problems at the end. All right, so a transformation is a change in the size, position, and or orientation of a figure. Should have made these blanks a little bit bigger for myself. So it's a change in the size, position, and or orientation. Now we have some special names for what we call the original figure, as well as the figure that we're left with after the transformation has been performed. The pre-image is the initial figure, while the image is the final figure. So when you start with something, we're going to call that the pre-image. What you end up with after you perform the transformations, we are going to call the image. So they both have image in their names, but one is the pre and one is just the image. Okay, let's start off with the translation. informally, this is known as a slide. So the definition is a transformation where all the points on a figure move in the same direction and the same distance. So they move in the same direction and the same distance. One of the demonstrations I would do if we were all, in a classroom together, I would just take a step forward, right? And you could do this, wherever you're sitting watching this, but if you take a step forward, every point on your body has moved in the same direction, right? Let's say you move 1 meter forward, right? So you take a step that's equal to 1 meter. Well, once you take that step, every part of your body has moved exactly 1 meter in whatever direction you took your step. And they've all moved in the same direction, right? The points on your head haven't moved forward while the points on your leg have moved backwards, right? After you've completed that 1 meter step, all of the points have clearly moved in the same direction and they've all moved the same distance. So that's what a translation is, or a slide. You could also think if you I don't know what you have in front of you, but maybe you have a mouse in front of you. If you just move the mouse, if you push the mouse forward, right, without spinning it, without flipping it over, if you just push it forward, that would be a translation. If you put a piece of paper on a desk, right, and you just slid the paper forward, or you could slide the paper to the left, slide it to the right. As long as you aren't rotating the figure or flipping the figure or the paper over, that is a translation. Let's talk about what this notation means down here. So this right here would be our pre-image. And this right here would represent our image. I guess you know what, I'm going to redo that because that's confusing based on what the colors on the on the document say. So we will do blue for the pre-image. So I can get my pen up here. There we go. So we got a pre-image here. And we have a post-image here, post-image. Just called an image. Excuse my incorrect vocabulary. So they have a square, or it may not be an actual square. We don't know if those are right angles or if the sides are all exactly the same, but we'll just call it a square for now. We could call it a quadrilateral because it just has 4 sides. So if we have a quadrilateral and we just push it, right, up and to the right, well, the one that we start with, we just name it by its vertices, right? JKML. After we have our image, though, after we move the quadrilateral, that's a new figure. So we don't want to name it with the exact same vertices or points as our old figure, right? Because it's different. It's in a different location, etc. So we put these little tick marks, right, that you can see here. We put these little tick marks right next to the letters, and that's read as J prime, K prime, M prime, L prime. We just call those primes. And it's actually something, if you ever take a calculus course, you'll see these primes show up again. So for the new image, we're going to put a little tick mark next to each letter. We use the same letters, we just add a tick mark. If we wanted to go further, let's say I pushed this figure up again, but let's say I just pushed it upwards instead of to the right. I could label my new figure. But I don't want to use just the regular letters, and I don't want to use just J prime. So what I'm going to do is I'm going to say J double prime, K double prime, L double prime, and M double prime. So as you continue to perform new transformations on this figure, if you want to see each individual step, you need to label them with different amounts of primes. And the farther you go in your the farther you go in your set of transformations, right, the more primes you're going to have. All right, so for each new transformation, add an additional tick mark to your letter. And the way, I think I already said this, but the way we would read this would be J double prime, K double prime, M double prime, and L double prime. All right, let's move on to the next vocabulary term. We won't spend as much time on that one. Now we have a reflection. This is a transformation across the line where the points on the pre-image are the same distance from the line as the corresponding points on the image. So let me make that slightly better. So let's take a look at our diagram over here, right? This line that we are flipping a figure over is going to be called the line of reflection. So this line of reflection is right here. And you'll notice that each corresponding point, so B and B prime, right, they are the exact same distance from that line of reflection. Same with A and A prime. They are the exact same distance, and C and C prime. That is the definition of a reflection. You pick a line and you reflect the figure over the line. And the new points on the image will be the same distance away from the line as the points on the pre-image. All right, let's move on to rotations. This is a transformation about a point, which we call the center of rotation, where each point of the pre-image and its corresponding point on the image are the same distance from the center, it should be of rotation, let's fix that real quick, center of rotation, and form the same angle with the center of rotation as every set of corresponding points. Wow, that was a lot to take in. And I think this diagram may be a little cluttered for our initial understanding of a rotation. So what I'm going to do is I'm going to go to a clean sheet of paper. I'm just going to demonstrate what a very simple rotation looks like. So for every rotation, we have to start off with a point that we are rotating the figure around. And this is called the center of rotation. For almost every problem you do in this class for me, your center of rotation will be the origin if we are on a graph. All right, so you'll be rotating around the origin. Let's pick a figure, and I'm just going to do a simple figure. I'm going to do a line segment. So I'm going to have line segment A, B. Now let's say I want to rotate this line segment 90 degrees around, we'll call this point P. I want to rotate it 90 degrees around point P. Well, here's what we do. And we're not going to do too many rotations by hand because they're very tedious, and there's software to help us do that nowadays. But if I was doing it by hand, I would first draw a segment. Let me do a different color. I would first, oh, now I'm on my eraser. Let's try this one more time. So I would just draw a segment from A to the center of rotation. Then I would mark a 90-degree angle. Okay, so I'm trying to, and if I had a protractor, I would get my protractor out and do that. But I'd make sure I had a 90-degree angle. Then I would see what this distance was. Let's say it was 2 inches. I would measure up 2 inches along this segment to figure out where my A prime point would be. And we can see it's going to be somewhere around there. So that would be my point A prime. Then you could erase these lines if you wanted to, because I don't need them anymore. And I would do the same thing with B. Okay, I would measure from B to my center of rotation. I would create a 90-degree angle, because I'm rotating 90 degrees. And let's say this length was 4 inches. Well, I'd measure 4 inches along this segment, or along this line until I got to 4, and I would mark my new point B prime. And then I could erase all my extra lines, or segments rather. And let me move my A prime out of the way. Then I could sketch my new segment. And you'll see, right, if I put these segments back in, that there's 90-degree angles formed between each set of corresponding points. Right, so the A and the A prime form a 90-degree angle when I connect them to the center of rotation, as well as my B and my B prime. Now you could quickly see if I had a very complicated figure up here, right, I would have a bunch of segments all over the place. But as long as I just matched up corresponding segments and continued to follow this process, I would come up with a new figure, right, that looks exactly the same as the old one, just rotated around that center of rotation. All right, but again, we're not going to perform a lot of rotations as let me rephrase it. We're not going to perform a lot of rotations using this method. There are some other ways that we can rotate when we're on a coordinate plane, where we don't have to actually get out a compass and a ruler and measure. But you know, it is an interesting thing to think about because you know, back in the hundreds or thousands of years ago when they were first discovering these topics, they didn't have all the cool tools we have today to perform these rotations. They had to use they had two tools to use. They had a compass and they had what we call a straight edge, which is essentially a ruler without all the markings. So again, I don't want to go too far into this, but they were able to do very complicated things in geometry with very simple tools. Okay, let's go back up and discuss these three. Okay, so we could think about the similarities between these transformations and the differences. And what I would do is I would pause the video and do that. Write down some similarities and write down some differences. All right, so I just put the main similarity up there, and that's that all transformations kept the pre-image and image the same, or we could be more precise and say congruent. Two things we can look for, right? The size of the figure never changed. The figure never got bigger or smaller when we did a translation, reflection, or rotation. And the angles in the figure never changed, right? So those two things are key. Some differences, the orientation changed for both reflections and rotations, but not for translations. And the transformations are not all performed in the same manner. So there's different ways to perform the different transformations. If you're unsure what I mean by orientation, so let me scroll back up here for a second. Right, for translations, right, you can see that the pre-image, right, JKLM, is positioned in the same manner as J prime, K prime, M prime, and L prime, right? It's not twisted. It's not, flipped over. The letters are all in the same, the figure is in the same relative position as it was when it started as far as where the vertices are, right? J prime is still in the top left, M prime is still in the top right, etc. That doesn't hold true if we look at a reflection, right? If we look at the pre-image for this reflection, ABC, well, the A is in the bottom left, but if we look at the image, A prime is in the bottom right. So you can see that A and C, or A prime and C prime, have essentially switched places from where A and C were. So that means that's what we say when the orientation has changed. And the same is true for reflections, right? If we look down here, this pre-image, the blue, right, is a rectangle where D and D are straight across on the bottom, G and F are straight across on the top. When we come to the image, well, now it's been twisted a little bit, right? There's no 2 points that are straight across on the bottom, right? They're now at angles, right? It's been twisted a little bit, so the sides are at angles with the horizontal rather than parallel to the horizontal. So that's what we mean by change in orientation. All right, let's think about what this means then. So because these transformations keep the figure the same, right? These are actually called rigid motions. All 3 of these transformations. They have another special name. They are called rigid motions. This is because all these transformations preserve distance and angle measurements. i.e. the pre-image and image are congruent. So the distance between corresponding points stays the same, and the angle measurements between the different segments will always stay the same. All right, so these are called rigid motions. You can think of something that's rigid, right? Like a rock, you need something that can apply a lot of pressure to be able to change a rock into some other form, right? So if you pick up a rock and you throw it, the size of the rock is going to stay the same. It's not going to become bigger. It's not going to become smaller. It's not going to, if it's a circular rock, it's not going to suddenly become a square when it hits the ground or hits the water, hits another rock, because it's rigid. So that's what rigid motions mean. The figure stays the same. It stays congruent all the way from the start of the transformation until the very end. All right, let's see about doing 1 or 2 practice problems. This video is already over 20 minutes, so I don't want to go too further. I think these next few you can try on your own. It just says identify what type of transformation is being used, so write down translation, reflection, or rotation. We will do one of these though. So here, we'll do number 1. It says apply the following rule to triangle ABC. And we need to think about how to read this, right? So we're going from a coordinate, and then we're adding 3 to the x value, and we're subtracting 5 from the y value. So a couple different ways you can do this, right? You can write out the coordinates. So for A, we have -4, 5, and something I like to do actually to keep everything situated or organized is I just like to write out the coordinates right in a row, because if you have a lot, then this can be helpful. B is at 1, 4, and C is at -1, 1. So when I perform this transformation, right, I should get a set of 3 new points. We're going to call those A prime, B prime, and C prime. And now I just need to figure out where those new points are. Well, my rule up here says add 3 to the x value, subtract 5 from the y values. So if I add 3 to -4, I get -1. If I subtract 5, I get 0. For B, I get 4, -1. And for C, I get 2, -4. And then you just need to go ahead and graph these new points. So I will graph this new one in, let's do pink. So I have -1, 0 for A prime. I have 4, -1 for B prime. And I have 2, -4 for C prime. So you can see that this was a, well, take 10 seconds if you're unsure what type of transformation this was. This would be a translation, right? This figure was just pushed down and to the right, but the orientation stayed the same, right? A is still in the top left of the figure, B is on the right, and C is at the bottom. So the orientation didn't change, just the position. You can do the same thing for number 2. I encourage you to do this the same way. Now, some students like to just count the blocks, right? So I showed you the method I prefer first. The other method that students may discover or that they may revert back to is I'm going to start with A, and they're going to count over 3 and then down 5. Right? And they're going to do the same thing for B and C. 1, 2, 3, 1, 2, 3, 4, 5. And for C, 1, 2, 3, 1, 2, 3, 4, 5. Again, positive meaning you would either go up or to the right, and negative meaning to the left or down. Now here's the thing. When you have a graph that is spaced out by single units, and you're not moving something, hundreds of units in one way or another, this method works okay, right? You can count to 3 and count to 5 fairly quickly. The problem is, what if that was x plus 2004? Right, and y minus 99. Well, you don't want to sit at a graph and count all those units. Your graph may not even be marked off by single tick marks. The jumps may, it may be marked off by 10s or 20s or 100s, right? And it's going to be much harder to get a good graph of your image if, the numbers are much larger or if the graph is not marked off in units. So stick to this method over here. I know it seems a little bit more tedious, but that is always going to work, whereas the counting method, it really just depends on what type of graph you're given and the size of your numbers. All right, I promise we're almost done. We're going to do one more. I want to talk about reflections. Same type of idea. So it says the coordinates for the image of triangle ABC after a reflection are A prime, B prime, and C prime. So it gives us the coordinates this time, so we're just going to label them. 4, 4 is A prime. B prime is 1, 2. And C prime is 4, 1. Then we can connect. And notice that this cannot be a translation, right? If I just push the pre-image upwards, well, C is only moving 2 units, right? While A would be moving 8 units. And for a translation, each point has to move the exact same distance. So that's why it's not a translation, just in case we were thinking that it was. What we do need to do is think about where that line of reflection is. What was the line that they flipped or reflected triangle ABC over? And you can take 5 or 10 seconds to sketch it in yourself. But that line would actually be the x-axis. Now it doesn't have to be one of the axes, but in this case it was. So you're going to do the same thing for number 2. Label your new image and then try to figure out where that line of reflection is. All right, and then sketch it in. All right, that is going to do it for this video. I know we went a little long, but we did go off on a couple of what I thought were interesting tangents, and hopefully you found them interesting as well. Feel free to try the rest of the problems. We will look at them the next time we have a discussion together, and that's going to wrap it up. So enjoy the rest of your day, and I look forward to seeing you at our next video.